And welcome to another episode of Adjunct of Computing.
We're back!
We're back to discuss the computer that is a computer that is not a computer. Metadata, I believe, is the name.
Wrong.
I have it on good authority.
It's Mad Ida.
I think it's very funny, too, though, because you say maybe it's mad, like you say it's not Metadata specifically. I always looked at it and heard Medita in my head. So there's a plethora of opinions on this.
Well, like I said in the episode, I was calling it Mad Ida because specifically the Northrop brochure says to pronounce it like Mad Ida.
Yes, which is great to have like that kind of sourcing. It reminds me of like we can figure out the pronunciation on Old English because of poetry, like that kind of thing.
Oh my God.
It's not that good,
funny.
but it feels like it rhymes with something like that. But yes, so Mad Ida. I have no notes this time, which I think means it's going to be an extra good episode, honestly.
Easy.
If history is anything to go by, which on this channel, it is. It's what we do. Anyhow, so Mad Ida. Let me actually take the reins a little bit this time.
Yeah.
Because...
what do you remember from the episode?
Yeah, I think that's, we should do that. That's a great way to like lead into this. So what I remember, the hot points that stand out to me is it is a disc and ball integrator that is made out of a magnetic drum and is also digital. And it is a computer, but it's not a computer, but it is a computer. And context is everything. And it was made to blow shit up, I believe.
It was made to correctly blow up the enemies of the American state. Correct.
Yes. Oh man, I bet for like and I know this is definitely a big contingent of just nerds, but like military technology nerds. I bet like Snark is probably a great goldmine itself of interesting stuff.
Oddly enough, when I started this episode, I watch a lot of surprise aerospace history on YouTube. Yeah, now my wife gets angry on road trips. We have a one aerospace museum per road trip rule because I've broken that before and she's been miserable. I have a photo of her just like glaring daggers at me in front of an A-10 Warthog at like the second aerospace museum we've been to in a day.
The plane that will shoot itself backwards?
Yes. Anyway,
let's not go down that.
When I started this episode, I'm like, I bet there's a documentary I can find on the Snark project because it's the first cruise missile. No. There's like archival footage, basically like press video from Northrop, and there's like bad auto-generated AI videos talking about Snark, but no one, or at least I couldn't find a documentary about it, which kind of bummed me out because, politically, but just technologically, fascinating program.
I think that's generally the thing with military history. We rub into it every now and then, and that is the thing.
Yes.
But interesting.
Yes.
But yes, cruise missiles as a whole thing, just a fascinating dead-end technology. But the best part is trying to figure out, as you were saying, where to send that cruise missile, or rather, how to tell the cruise missile you are slightly wrong and you need to go this direction to get to your destination.
The missile knows where it is because it knows where it isn't, right? Like that's literally the meme, is they're making a machine for the meme.
That is literally, I think that's like the best definition of a servo mechanism that I've ever heard. If anybody needs to ask me what a servo mechanism is, I'll say it's a mechanism that figures out where it is by figuring out where it isn't.
Yeah.
Because it literally is.
That's not entirely wrong. That I have, no notes. No correction. Well, yes, correction. Ha.
For people who are wondering, why are we talking about Snark? And I mean, presumably you've watched the episode, but I mean, if you've missed it or, forgot, the whole thing here is that Mad Ida, which we'll get into more details about here, and we'll chat about more, was, as discussed in the episode, partly developed to calculate tables for a guided cruise missile. And it's also fascinating because, again, a big part of this is Northrop wanted to compute this stuff accurately ahead of time. And this is also at a time, because we're talking late 40s, early 50s, that you can't put a computer on a cruise missile.
You can't just do it.
But they were like, let's not pay attention to that part and just develop a computer for a cruise missile.
It's also really funny in the sources, because Snark ends up using an analog device.
Does it really?
Yeah, it's full analog. Don't ask me questions about it. I was just reading about the failed attempt. But in the primary sourcing, it's like really ambiguous if they ever thought that Mad Ida could fit in Snark. Like the main paper I was using from 2003, one of the authors is like, yeah, there was a brief window of time where we thought it was possible. And then it's like, next paragraph. It's like, no, I'd love to hear about that window of time.
Well, and perhaps maybe this was mildly influenced by the engineer's desire to can the whole project and just make a computer.
Yes.
Perhaps they said, maybe we could fit this in. And then they said, let's just can the whole project. And then they, I don't know, got fired or something, whatever happened next. But yes, a fascinating story. And one of the fascinating things that, I mean, honestly, this is one of those episodes, you get them pretty regularly because it's a small cast of characters, as we've said today. Maybe not a small cast of characters, but there are some prominent
early on,
characters.
There's like 10 people that know what a computer is.
Yeah, that really is what it is. And when you go back to these older period things, you're dealing with that crew. And Bynak. Bynak is the first thing that's on my mind because...
Yeah. We found it. We got to the actual origin of Bynak.
Which is great. The fact that, again, to recap, if you missed the episode or forgot some stuff, that Bynak was supposed to be like the pilot program for making a computer to put on the Snark. And again, I vaguely knew about Bynak, but it wasn't until I started doing this show and Sean was like, no, you seriously go look at a picture. And so I did seriously go look at a picture.
Two computers.
And it is just two refrigerator-sized CPUs just next to each other in a room with what looks, I think the best part is with what looks like a vent hood above them, like a commercial kitchen vent hood. Yeah.
Two of them.
Each one going up into a manifold. And I mean, because that's literally what it is, because it's the air conditioning. Anyway, and that was the intended thing to go on this cruise missile.
Well, it wasn't intended to go on it. That's one of the things that is incorrect, or I want to be careful with my language because I know in the episode I'm like, oh, Paul Ceruzzi was wrong, and that's not strictly accurate. There were sources that came out since Paul Ceruzzi wrote a very popular history that includes a story about Bynak and Mad Ida. And because of that, like the common story that Ceruzzi recounted was that they got Bynak because they were going to shrink it down and use it on the missile, and it sucked, and it never worked actually, and they moved it and it arrived broken, and everyone was so mad that they made Mad Ida, and that's not really the case. Bynak was a test article. They got it specifically to test out computing ideas, not thinking that it would miniaturize down and magically fit inside a missile.
Right. It's just like you got to start somewhere. And like I very much get that from an engineering perspective in that like if you think about nothing else and you just take it at face value, you're like, well, that's crazy. But especially at the time when things are moving fast, this is the new technology. And I mean, you can see it in just the invention of something like Mad Ida, which is a single purpose computer, which I know is one of your favorite topics, and I think it's ripe for conversation here.
They're so weird. They're fascinating.
You know why something like Bynak is big is because it's a general purpose computer. That's the thing about general purpose computers. They're general purpose. They can do anything, but as a result of that, or as part and parcel with that, is that it requires a bunch of hardware to be general purpose. Whereas you can strip out a lot of things to solve a specific problem using the same mechanisms, but without all the control circuitry to handle a bunch of different instructions.
Generality is really expensive. I know I'm already going off on a tangent. But
that's all we do.
It is. A few years back, actually at VCF SoCal, everyone should go. Great event. There was a guy who built a wire wrap computer from scratch using TTL logic. Just really cool machine.
Are you?
And
My mind was vaguely elsewhere, and that caught me. Is this the Bill Busby magic one?
no, this is a different one.
Oh, it's a different one. I just love
Yeah,
Bill Busby,
yeah,
and
he's
I know
using-
he's been going around the last year or two.
So I forget who this guy was. I could look it up, but his machine was really interesting because he just kind of dove in. It's like, oh, I'll figure out how you make a computer. How hard can it be? And he was giving a talk about it and giving demos. And while he was going through the design, he's like, I figured out that it was actually a lot easier to make a very, very simple computer with what I now have come to learn is called horizontal microcode. And he just like stumbled upon the idea of microcode like from first principles and was like, wow,
You gotta love it.
that I have my circuits just strip away if I have microcode. But that's the cost of generality. Is to have a truly general purpose computer, you have to either have something very subtle and sophisticated, or you have to have two giant machines with two cooking hoods and an AC unit.
And I am so sorry. I'm just such a scenester, and I have been nerd sniped here because this used to just be like, I think I've talked about, maybe I haven't, that like I was really into the homebrew CPU web ring, and I don't know if you were.
Yes,
I think we've talked about this
I think
before.
you've mentioned that. Yeah.
Busby was on it. So now I've got all these ones that are in my head, and it's not the topic at hand, but I'm just. Was it BMOW? Was it Big Mess of Wires?
No. This is
Just because
different
I
one.
know he's West Coast. Okay, I will stop. That's not the topic. That's not what the people came here for. So, let's talk about the single purpose, special purpose computer thing. Because I know you like it, and I think firstly, this is just one of the things that I like the descriptions and the amount of information we have on Mad Ida that gets presented in this episode, in as far as the description of how it works and whatnot, because sometimes one has more, sometimes one has less. And I do get the impression that you have less than you would like, but still it's more than I would have thought maybe. But just that I get like a kind of good idea of what this thing is doing.
Yeah, so the interesting part is we have very few technical sources on Mad Ida. We have a preliminary progress report, we have a brochure, and we have, it's not even like an operations manual. It's like a 3-page on here's how you run it. And that's it. Everything else
The user's guide?
No, we don't have a user's guide, which makes me upset. Like I want to know how, like, the brochure explains how to program it pretty well. I'd love to have like the actual manual that Northrop expected people to use to learn how to program it.
Right.
Because that tells you a lot about like the headspace and the thinking around the machine. And we don't have that, but from the progress report and oddly enough the brochure, like it explains really well how it functions, like on operation principles, and those line up with the primary sourcing we have with the oral histories and the 2003 paper, which you love to see. But that's enough to reconstruct how the machine worked.
I do enjoy, I don't exactly know how I would describe the category. There's definitely a description for it, but the more into this category of like professional equipment you get, the more your brochure becomes just like literally here's what the machine
mini
is.
manual.
Yeah, like and the big thing that gets me is just I don't know, things like you stop having like standard interfaces on things and stuff. Now, this is back in the time where there weren't standard interfaces to anything, but Mad Ida makes me think of it in the way that you describe it, of like, you're given this thing and you're expected to connect it to other stuff because you know what you're doing. And I just feel like there's a certain class of professional equipment that is, I mean, still just like that. You know, you get the box, there are connections on it, you know what you're doing, or you pay somebody to know what they're doing. And like, to anybody else in like the prosumer or consumer space, it would be like, you're selling me a thing that is like basically not usable. But like when you hit a certain class of technology and professional sphere, you get given like a box, and it's like almost a benefit that like, this is basically a part of a thing. You finish it.
Yeah, I was about to say I have no experience with that, but then I started remembering way long ago in my career, a vendor we worked with at an internet radio company that would just ship boxes without any instructions. It's like, oh yeah, you're like, the serial interface is standardized. You're supposed to know what standard it is. It's like, yeah.
If you don't, you shouldn't be buying this.
Well, and also the historical context is something to consider here, because the brochures from I think 53, they end up making and selling 6 Mad Idas, which that's a whole different thing that I want to discuss another time. I plan to. But in 1953, you can't just say in a brochure, here's a computer that has 4K of RAM.
Right. Well, I mean,
what does that mean?
What do they?
No one would know what that means.
What do they say? Because it's an interesting thing in that this machine sits in a place that is very clearly spelled out in the episode, that it is kind of lab equipment, kind of a calculating machine. It's an analog computer, which analog computers often sit in that same space where they're often used, they're a plug-in unit almost. They can be used in lab equipment for you plug them into the rest of your testing apparatus or whatnot, or you actually use them for simulation. Either or, they serve both purposes.
I have the beautiful brochure, Mad Ida, the new desk-side digital differential analyzer, patents applied for. So, first page is literally, what is Mad Ida? Mad Ida, oh yeah, here it is. Rhymes with Mad space Ida, like the name, is a digital differential analyzer employing a magnetic drum type of memory. And then they just describe what the acronym means. And that's how it starts.
That's you hook them and you've sold them.
Well,
I do just enjoy, because when I was hearing in the episode, I understand it. It obviously makes sense. It's not that dumb, but I like that it is literally MADIDA rhymes with MADIDA.
Yes.
now that's some copy right there.
No, that oh my god, that tripped me up when I saw it, because it says rhymes with Mad Ida. I'm like, well, yeah, it does. I'm like, wait, no, that's just the same thing. What do you mean? That's an illegal rhyme.
Yes. This reminds me of teaching my kid that you can't rhyme a word with the same word.
Well, why not? Why not, Joe?
I mean,
Northrop Aircraft did it.
That's true. And you figured it out. It worked.
Barely know how to speak English because they only know computer.
To back up a second, when I was talking about the way that it gives me enough of an idea, at least maybe even the evolution of the thing gives me part of the idea of how it operates or its operating principle. You give part of it in the what it does and but also just the history of the Dida going into the Mad Ida really gives me an idea. This makes sense now. I mean, it's implicit in the episode, but that they take the vacuum tube registers from the Dida and they swap them out for tracks on the drum. That's the whole middle of the story. And so now I get it, because as it spins, you're picking up a bit every time it's coming by the read head or whatever, and that's accumulating or running through whatever, and then accumulating onto another track or whatnot. And I'm sure your plug board is just connecting amplifiers from heads to the other amplifiers from the other heads, or the adding incrementing circuitry that's attached to those heads, and that's it. I mean, it totally it makes sense, because really all integration is it's just adding.
It's just
over
adding
time
little chunks,
right?
So what's one of the things that's interesting in the gap in sourcing is we don't actually have a photo of the plug board for a Mad Ida, which now I'm hoping next weekend when I'm down at VCF at the Computer History Museum, they have actually the unit that the episode's about. They have the first Mad Ida on display, or they have it in their collection. I don't know if it's on display right now.
Considering they sold 6 of them, having any is pretty cool.
Right. And so they have the original one, the one that John von Neumann saw, that was in the Princeton Inn.
That still has the aura of gin about it.
One can hope. But I'm hoping it's on display. I was posting about the episode on LinkedIn, and Dag Spicer, who's one of the curators at CHM, hit me up in the comments and was like, "We have one in our collection." So
now that's a flex.
That is a flex. I'm trying to find out if they have it on display, and if they don't, see if I can ask very nicely to see it, because I want to take a photo of the plug board. I really want to see what the interface is, since we don't have a manual describing how to plug it. It just says, oh yeah, you can figure out how to wire it using a plug board.
You'll get it.
Yeah, part of me is really curious if they're just using like a plug board off a punch card machine or something that people would have known how to use at the time. And so it's like, oh, we don't need to explain it. Or if they just ran out of time and didn't want to bother, you know, because a lot of times when stuff gets glossed over, it's because like casting out nines, right? Like, oh, it's like casting out nines. Next paragraph. Everyone knows what that is. You learn that in grade school.
It's part of the culture, as it were.
Yeah, exactly. So want to see the board.
Yeah.
Want to view it.
I mean, I feel like early computers like this, you're always going to draw the parallels, bring up ENIAC and stuff like that. But the plug board just gets into my head. Understanding like the pulsed signal nature of a bunch of that stuff. Like, again, I mean, I don't know 100%, but almost guaranteed what's traveling over those plug board wires is you're connecting pulses coming out of one unit that are going into another unit.
Well, and especially because it's cyclical reading off heads on a drum, you're going to get a pulse chain.
Yeah. So, I mean, like once you get that, these plug boards make a bunch of sense. Cause I used to wonder like, okay, so what are you like, you program it with a plug board. What is that? What is it doing? And I just like to bring that up because I think it's a very non-obvious thing until you understand that it's like a very different thing, period, than what you'd think from programming. It's that, like analog computers, what you're really doing is or again, if you have any familiarity with like analog synths or stuff, you are patching units into each other and you are feeding a signal that is a trigger for something into another thing is what's going on.
Well, and the other thing is, at least in my opinion, as a dangerous freelance historian that no one should actually listen to, there's not really accessible coverage of what plug boards actually were and how they were actually used. Because if I show you a photo of one, like I have one on my wall right here that I'm looking at, I can just grab it.
Do it.
It's just a grid. Like it's just a grid of holes.
Right.
And like there's labels on it, but the labels are something like 5B blank column detection entry 2s. That means nothing.
Well, the good thing is you got your manual that comes with it. Yeah, that tells you should understand the plug board.
But that means how do you explain that to a modern person without sitting them down with the manual and being like, look here, kid.
Well, like first it's like, here's what the subunits on this machine do. Here's their inputs and outputs, and here's what happens when this kind of signal goes into this kind of output and into this kind of input. And
it's very, very difficult to explain unless, like, my opinion is the way to do it is historically, right? You talk about how it was developed, you talk about how it was used, and that by way of explaining that part, kind of like a cultural or social history, you're implicitly being told how it works. Because to explain like how they cobble together a tabulator, you kind of have to explain the actual cobbling bit, right? So you might not have a working understanding, but you can start to appreciate, like you were saying, oh yeah, there's subunits that are connected and sending pulses instead of like I'm wiring up a bus.
And like I said about the DIDA to MAT-IDA thing too, is that going through the history of the development of a thing also gives you kind of an insight in, here's the logical next step to that, which a lot of times when you're in the room building the thing or iterating on the thing or improving another thing, it's, I mean, maybe not obvious because these are, problems, you're working on solving them, but you can get the idea, especially us combined with after the fact of what the thing is, you can see what their problem was, which often isn't obvious after the thing is built, but after it's built, how that problem was solved is then a little more obvious. So now that you're coming at it from both sides, you get like that, they came to this because their problem was this in a very specific way that only studying the iterative process really can teach you.
Like with MAT-IDA, especially if you just say, oh yeah, it's a digital differential analyzer that uses a magnetic drum. That sounds crazy. That doesn't fit together at all, right? Those are such different technologies.
It's good because historically, like just when you were saying describing it as, here's this catalog for a digital differential analyzer, right?
Yeah.
Is that like, that's also a thing that people had various versions of at the time because A, computers don't exist. And that's another thing, you know, we take for granted. Yeah, you have your EDA program or something, or your, you know, your CAE program that's doing finite element analysis or something, which is all,
that wasn't a thing.
It's all tons of differential equations. And what you've got going on in that program is effectively a bunch of little differential analyzers. But we don't, there's such a commodity part of that program or whatever that we don't care about that unit per se anymore. But back in the day,
that was
just having a machine that could do that was
Yeah.
crazy helpful, and that there was actually a market for that particular type of device, and people were working on those particular type of devices in terms of
even
analog
being
computers,
able to
in terms
build-
of Vannevar Bush.
Yeah, the man that keeps showing up.
He just keeps showing up. But I mean, that's one of his big claims of fame, is building a particular differential analyzer. You know, it's just a thing.
Well, and just the component that can, like, I rag on ball and disc integrators because they sound like magic, right? Like in my chart.
But if you look at them,
things,
you immediately are like, I get it. Like,
yeah, you can see how it works, but like just having a device that can solve that can run an integral, right? That's wild.
Any computation using a physical process, I just think is great. Especially a continuous physical process.
With the switch from the ball and disc to digital, that's like physical device aside, that's really an amazing technology. It's a huge leap that, like you were saying, we take the fact that you can integrate on a computer, we take that for granted today.
It's not even a discussed part of the package.
Yeah, it's like a computer does math. It does math really fast in every way you could ever want. But in the 40s, they're still building up every little device that can do that and all the methods and mechanisms to do that.
Yep. Great.
It's just neat.
It is just neat.
You should make a ball and disc integrator, Joe.
I tried making a tape head one time and it barely worked. I can't be given projects like this. So, let's see. Other good... of course, the thing is, when you're talking, there's nothing but topics spring into my mind. And then the second we hit a break in conversation, they're gone.
That's classic.
That's classic. I mean,
there is the gin.
The gin. How could one forget the gin?
That's something that... So we were talking about this a little bit earlier this week, Joe. But I've been trying to find if it was a well-known fact that John von Neumann made really strong martinis.
I feel like there's just something like mid-century classy nerd feels like a martini. Like that reads correctly to me.
I mean, it makes sense. I wasn't surprised when I read it, but how it's delivered is it's in that 2003 paper. The author quotes one of his colleagues who gives this really extended quote telling the whole story about meeting John von Neumann, meeting Johnny. And he says that martini thing just kind of like, oh, you know, von Neumann was notorious for making gin martinis that were just gin.
It was just the thing.
Yeah. And so I've been trying to find anything that says that, and I haven't been able to. So I wonder if it's just like hidden in some oral histories somewhere that haven't been digitized. A bunch of people being like, oh yeah, we went over to dinner at the von Neumanns and oh my God, I had to walk home.
The good thing here is that we have a platform on which we can disclaim that we do not know, we cannot source it beyond that one thing. And then just go ahead and choose to believe it. And from then on out, it's been disclaimed.
I'm fine believing it. There's some, I haven't put together the full constellation yet, but there's, I mean, I know it's the mid-century. Alcoholism was a very different kind of beast.
Oh, it was great. It was how work got done.
Don't say that. But there is some like funny connection with heavy drinking and early computers that I have like 3 or 4 data points. I need to get more, and I think there's like some story that could be told there. But
the curve of computational alcoholism?
Something like that. There's Well, because there's John Atanasoff.
Okay, run me past that one, because the only one that I have on my mind is...
do you not know that story?
No. So give it to me in just a second, because I was just going to say the only thing that's really on my mind is the
Alan Turing
and the gin delay line.
Vat. Imagine if your gin vat mumbled at you while you were trying to program.
I think that would be nice.
So the John Atanasoff, he's the one that made the Atanasoff-Berry computer.
Right.
And how that happened, it was in the 1930s. He needed a machine to do linear algebra, and he's like, I'll make an analog computer. Because it's the 30s, that's the answer. He fails miserably. It's not right. So he's like, well, I have a punch card tabulator. I have a multiplying punch. I'll modify it. And so he starts trying to modify it. He can't figure out the circuit, so he calls up IBM. And he's like, hey fellas, can you send me a circuit diagram? And they're like, what? And he's like, well, I'm trying to modify a tabulator. And they're like, no, we'll send you something, though. And they send him a cease and desist letter.
Nice.
And it actually comes out during some of IBM's antitrust lawsuits in the late 60s that they had a dossier on Atanasoff because he was trying to modify a tabulator.
That madman.
It turns up in Discovery. There's a filing cabinet with a file that's just like enemies of IBM, John Atanasoff, some guy in Iowa.
Gotta be stopped.
So he's just really frustrated, and he's trying to figure out how to make a machine that can do linear algebra. And so it's the winter of 1933 in, I forget if it's Illinois or Iowa. I think it's Illinois. It's the one where at the time it was a dry state. So he bundles up, he gets in his car, and he just starts driving east. Mm-hmm. And as he puts it, every time he starts thinking about a computer, he accelerates until he stops thinking about a computer. It's icy, it's cold, and he eventually crosses the state border into a state where you can buy liquor. And he's like, well, I have a good idea. And so he goes to what he calls, and he doesn't budge on the lingo, a roadside honky tonk. And he goes and gets a drink, probably more than one drink, and on a napkin starts figuring out I think you probably have to use binary. And if you do that, well, I bet you could use vacuum tubes. If you use vacuum tubes, that's kind of like a logic operation. And so he's one of the people that independently comes up with the idea of using vacuum tubes as a physical embodiment of Boolean algebra. Just drinking in a honky-tonk at midnight in the dead of winter in the Midwest. And then he drives back to his office.
Again, truly not endorsing anything, but sometimes this is the way things are done. That's how you invent something, man.
Yeah, I mean, especially in the 30s. That's just what you do, I guess.
I mean, we came off the last episode talking all about the counterculture influencing the computer culture, and I mean, if Steve Jobs can be out there dropping acid, coming up with computer ideas, then God bless him, Atanasoff can be on the roadside having a honky tonk, doing figuring out his plans. Okay, so I did manage to remember a couple that popped up, and I grabbed onto them. I pulled them out of the ether. One is just a thing I love about this episode is because I did not see this coming, and it's fantastic. And I think we need to linger on it for a second. The independent development of attaching tape to a drum.
Yes!
It's so good. I cannot believe it's not surprising because it's I independently had that idea. We talked about this. I was like, that's a thing I could do. Put it on a tin can, spin it with a motor. I could bet that would work more or less. And that was independently, there was just another group of people. And then you've got the Toluene trick. And then you've got speaking of things that you need to have build your own little charts and stuff on.
My God,
one is all of the independent ways that people figured out how to hack magnetic media onto a spinning disc. Toluene and then dissolving it in potentially acetone and squirting it on.
Now, now that we're having this discussion, it's making me think about, like we were saying earlier, the casting out nine, stuff that's culturally lost. I wonder if a lot of that knowledge was just people had already learned how to splice tape, and that gave them like the tools and adhesives to be like, I can put a tape on anything. I'll put a tape on a dog. Like I have the little brush and I have the stuff. Like maybe it was just an access thing, which made it really easy to be like, oh yeah, well, we have tape. We want it to be on a drum. Well, we have, a kit for splicing. We have the adhesives. You just adhere it to a drum and then you're done.
Okay. Insane, totally incorrect headcanon.
Okay.
As we do.
Yes.
You don't know what the solute.
The solvent?
The solvent. There we go.
Yeah.
You don't know what
was it gin?
You don't know. Oh, different headcanon, but I like it just about as much. These guys knew each other somehow in a way that's not documented, and you know what the solvent was? It was toluene. And he said, if you run it through toluene, you'll get a toluene solution. You can put it right on there. I do not think that happened. But that's like a good, if I was writing a historical fiction book about banal things that wouldn't make for great reading, that's what I would put in there.
Yeah, that's making me, I kind of want to get some reel-to-reel tapes and melt them in toluene, gin, and acetone and see which I
You want to do this right now,
kit.
Sean, because I have reel-to-reel tapes and I have toluene.
All right, do it. Does it actually melt?
I can't do it. They're my friend's tapes.
All right. Well, I have an airbrush for personal use.
Yes. Let's not go deeper into that. If you
you
can figure out from this picture what Sean has an airbrush for. We're not going to tell you. This is it's like the hidden picture. I spy.
Magic eye.
Tell us in the Discord if you figure it out.
I could probably find some toluene. Maybe that is the solvent they used. And if that is the case, I wonder if toluene was just really... So going back to what I was saying...
toluene is silver polish.
If that was just common.
Yeah.
It's silver polish? I have toluene then.
Wait, let me pause because it's literally around the corner in a bucket. So we could put this to rest a little bit because...
show me the bucket.
We'll see if I'll get you my bucket.
Show me the bucket,
Okay,
Joe.
You have to entertain the people for about 30 seconds. Go.
All right, so I bought my airbrush at a pawn shop called John's Pondemonium. It was a very good deal. I was on the fence about buying an airbrush until I found a good deal on it. Now I love my airbrush, but I don't think I'm allowed to say what I use my airbrush for. Exercise for the reader, so to speak. I don't have toluene, but I do have a bunch of acetone. Also exercise for the reader.
I can't hear a dang thing you're saying. I hope it's good.
Oh, that's fine. Talking acetone, Joe.
That's some serious stuff.
It's not that acetone's not that nasty.
Don't attempt to polish a Game Boy screen with acetone.
That would melt it.
It would.
That would melt. Not
and
compatible.
You would be a dummy.
Not compatible with PLA.
Okay, I mean, cameras flipped.
Instant silver dip.
We'll see how this is in editing. Haggerty, instant silver dip. Let's see.
All right, where does it say toluene?
I mean, it's not actually going to say on here, too. I'm going to have to, look this up. It's just got instructions, precautions.
You're just going to have to melt things to prove that it's toluene.
This product can expose you to chemicals including thiourea, which is known to the state of California to cause cancer.
I mean, many things are.
It is. But, so I might be potentially totally wrong, but I have no idea why. Okay. Well,
I'm just going to try to melt cassettes in every fluid in my home, and when one works, I'll know it has toluene.
It was Diet Coke the whole time.
It's qualitative analysis.
Yes. All right. So I had grabbed two things out of the ether. One of them was independent discovery of getting
just putting a cassette
rust
tape
off
on
a tape.
Something.
The other one is something. We've talked about. Let me just run through the things we've talked about so I can refresh my own memory. So we've talked about the Binac thing. I know that was. I mean, that's just great.
It's two computers.
I will say it just because it pops into my mind. It's not a topic of deep discussion, but the idea that we haven't really talked about at all here of loading, like calculating not on the cruise missile and then loading onto the cruise missile like right ahead of time is both so dumb, but also so of its time.
I don't think it would. Okay, to be fair, this was a theory that didn't happen. So who's to say? I don't think it would have been ahead of time. I don't think it would have been just in time. I think it would have been like when they manufactured the missile. Because it would be something, because it would be like a corrections table. It would be like a table to look up. So the sensors would be like, I know I'm here. I've moved like this. Calculate the deviation by like looking up cell 28 or something on the tape. It would be like a find your own adventure for a cruise missile.
That probably does make more sense because I was picturing more like, again, like calculating trajectory to the target.
That would be really funny, but I think that would also mean that you'd have to have a computer in the field, which at the time would have been impossible, or at least inconceivable.
Well, I just think it's great and of the time because that's like I'm not an ICBM expert. I know enough to be dangerous, which I feel like probably you're in the same boat, seeing as you said you have a big interest in these aeronautical things. But I know because like I think it's probably particularly hypergolic fuels, where there are a bunch of
the good stuff
families of ICBMs that use hypergolic fuels, and they are loaded in like just before launch.
Well, that's different because hypergols are dangerous.
Well,
they are very, very dangerous.
Are you telling me that the directions to blow up someone's home is also not dangerous?
All I'm saying is a reel-to-reel tape that has a bunch of nerd things on it isn't as dangerous as hypergols.
You underestimate the danger of knowledge, Sean.
It's just beep beeps. It's just beep beep stuff. Like,
hey, you know what else was beep beeps? Was Sputnik coming over everybody's radios. It went by dangerous. And it freaked people out. So don't discount the beeps. But no, not that I legitimately like have a like, oh, so it must have been just like that. It's just that seems like so like that lines up so perfectly in my head where it's like
that would be really
they jam in the thing, load the hypergols, and they jam in the, they load the tape at the same time.
They have like the most bizarre looking reel-to-reel cassette enclosure you've seen in your life.
Oh yeah. Well, military technology. It's all weird, all their own standard, chunky, crazy stuff. It's great. All right. So we've discussed that. Running down the list again. We have done BINAC. We have done, now I've talked about the preloading. Oh, and the preloading. This isn't like a huge conversation thing. It just reminds me of, I think people are somewhat aware, kind of not aware. It's like a 50-50 thing that, Apollo stuff, a lot of it was not done on the AGC. It's that they would send a bunch of like telemetry down, run it on like a 360 or something.
7090.
But they'd run it on equipment on the ground and then they would beam it back up. I know always Curious Mark has good stuff on that, but that's just on my mind, especially because he recently did a thing about the whole process, the crazy process of
I should catch up on his videos.
The guy who sits at the console and tells the computer to load the stuff from the other thing, which just tells a guy at another console to load the stuff into that UNIVAC and then give that UNIVAC the command to load it into the 360 and then send it, over some crazy link to Australia.
Was it actually a 360?
They have a bunch of stuff. And I mean, that is tough to say because, this is the 60s, so that's like when the 360 is coming out. So
this
like
is
definitely
late
Mercury
enough.
period. They're using 7
series
stuff.
I think I am thinking about Mercury or Gemini using 7090s.
I don't know history space which computer wins stuff very well. I just know that you're generally right. 360s are used later, and also I know for sure 7 series stuff is. I mean, they use IBM stuff from the outset because it's what's very available.
And no one ever got fired for buying IBM.
Very true. And it turns out they had a bit of a budget. But that just reminded me a bunch. Like it also makes the idea of like pre-calculating a bunch of stuff not that crazy because this is still, we're talking when we're doing the moon landing.
Right.
That's more than a decade past where we're talking about now. And even then, there's still, it's a much bigger project. There's a lot more stuff to keep track of, but it's still, you need big iron to do a bunch of heavy lifting, and then you can transfer it to do more stuff on a smaller thing elsewhere.
So running down the list.
Let's start again. See, this becomes not an issue. It becomes a shtick, which makes it fun. So we've done BINAC.
It's two of them.
We've done loading up. We've done just snark is interesting in general. We've done hypergalls, apparently, for no good. We've done Toluene. Gosh.
Plug boards.
We've done plug boards. We've done
Gin.
We've done gin. Mad Ida is a interesting study in here's where we're at. Here's a thing that like was not a particular topic that I had grabbed out of the ether, but just talking about how it is a weird thing that sits in a niche of being a computer and not a computer, right? Because that is really your thesis. And we kind of haven't talked about that at all yet. Here.
Yeah, we can talk about that easily. Nothing's a computer, Joe.
No.
It's all fake.
And I mean, we've talked about it before, and we will talk about it many times again in the future.
What is a computer?
Because whenever you get back into, when you get trapped back into the 40s, as so often happens to people, just in general, you know, I'm pretty sure this isn't just a you thing. That would be, it can't just be a you thing. I'm just going to start
wearing a suit with huge lapels.
Yeah.
The widest tie you've ever seen.
And pinstripes are making a comeback.
Ooh.
Yeah, and we'll all be drinking dry martinis. Where were we? What was going on here?
Computers and
I got lost in the 40s. But yeah, and also this ties in, we can talk a little bit about, because I never gave you space to, let's talk about special purpose computers in this kind of era. Because I touched on it a little bit, but that's one of the things about Mad Ida is tying in the whole thing of it doesn't work like another computer, right? You have the study of the computers available at the time, whatnot, with the spec tables, as you mentioned, and
it just doesn't fit.
Right, because what's happening is it is doing operations on the fly. I like that kind of that book ending a little bit, because you describe, that's kind of more at the beginning. You say, you know, the table's weird, and then by the end of it, you're like, I understand. Like, obviously, I understand this is an odd computer, so like, yeah, of course, it's described weird. But by the end, you're like, oh, because it's a special purpose computer that is doing a specific operation just every drum rotation. So it's actually doing, and this is the thing for me, keep that in your head.
All right.
I have trouble, so I want you to make sure that because it's a special purpose computer, it's actually doing it real fast compared to those other computers, because they have to go through a whole cycle of read the instruction, ready the memory location in the memory buffer, wait for a memory cycle or the thing to pass by or whatever, however your memory works. Pull the instruction. We haven't even gotten to, we don't have the instruction in anywhere useful yet. Decode the instruction. Get the first operand. Wait for memory to become available.
You have to have a program. You have to write a whole program to integrate, which is non-trivial.
Right. But even just speaking in terms of the operation, like
it's a lot
this special purpose computer, and it's how they end up being. This is why people Bitcoin with ASICs. This is exactly the same kind of thing that it is because you don't have the program. You just run it through that computational unit.
You are the program.
Right.
What I was going to say is that this is exactly what I find so interesting about special purpose computers is no two are the same. Once we get to general purpose computers, because of the Church-Turing thesis, a computer that can compute anything computable.
And that's why they're so boring, and we hate talking about them.
We, hate computers, man. I never want to see a computer again in my life.
I joke, but I think that's part of this, right? There is some truth to it. Is once you've said this is a general purpose computer, there's some interesting stuff in how it got there, or but the ancillary stuff is interesting, but you know what it can do.
Yeah, and it is kind of thought terminating because at a point it's a computer.
Yes.
It works. It's beige. We love it. We get angry emails on it. We get hate mail on the machine. But these early special purpose computers are completely different. They operate on totally different principles, but a lot of them still have similarities to general purpose computers. And so like with Mad Ida, the only similarity is that it uses a drum with binary data on it. and that's about it.
That's such a, I think it makes for a really good parallel and a ripe subject for looking into for that parallel, because that's how it gets to be, like I was saying kind of at the top, pared down into this thing that, I mean, it fits in it's like one of those, you know,
it fits
like
in a crate.
desk side kind of things.
Literally the desk. Wait, I got the brochure. It is the new desk side digital differential analyzer patents applied for.
That's right.
Yeah, it is a remarkably small computer, and it can be small. To your point, it can be fast, it can be efficient, because it is specialized.
Right.
You're not paying that cost for generalization.
Well, because again, to go through that cycle of, you've ripped out the whole, like even just the muxing, the matrixing hardware that switches where the data from the drum track is going to, what effect it's having, or whether it's being treated as an instruction or as data, if it's coming, if it's going, because it is the same hardware, a bunch of it. The drum is the same. It's got the same kind of stuff on it. In the sense of, even it's the same kind of binary pulse coded data that would be on a drum based computer. But you are hardwiring, you're closing shut the, all right, send this to the adder switch, and there's nothing that needs to drive that switch to close that connection. There's none of that. You just take that part and you throw it away and you solder the wires together, you know?
So here's a question, Joe. Are sequence-controlled calculators special-purpose computers?
I mean,
are they not computers
it's a
at all?
spectrum. It is a spectrum, is it not? Because
yes,
there are.
What was the spectrum we constructed earlier?
I mean, we're always constructing spectrums here and then immediately forgetting about them. But yeah, I mean, definitely a spectrum between like fixed function maybe and general purpose. And it is like, because I mean, of course, Mad Ida's not completely fixed function because they didn't solder all those wires together, right? They took some of them, they attached them to a jack, and you can unplug that jack and connect it to a different thing.
A mysterious jack that we don't know about.
Yes.
Secret Jack. That's his name.
Secret Jack that we will only be able to find by finding that dang manual.
If Dag Spicer agrees to let me look in the back rooms at the Computer History Museum, we might know who Secret Jack is.
You will find Secret Jack lurking in the back room. Wonderful. But yeah, so that's just, I think that's worth thinking about, because that's also, I think, a reason that these special purpose computers crop up a bunch at that time is because it takes a lot to build a general purpose computer.
Much.
It is, I think, one of the things that's implicit but not spoken about a bunch, because we haven't even really spoken about it particularly, is that one of the things that makes the whole stored program computer idea that comes around when von Neumann leaks
von Neumann
everything.
Doesn't leak it. Someone else leaks it.
I know, because you've gone over this. But again, wrong headcanon, which I have plenty of.
The factoid is Johnny's out on the street handing out drafts.
Yeah, he was like, check out these ideas that weren't mine.
Have you ever considered organs of computation, perhaps?
But anyhow, one of the big things there is that it simplifies a whole bunch of stuff, because like you've condensed your instruction thing. Your instruction storage mechanism is the same thing as your data storage mechanism. And so like that, like it simplifies the whole computer by a bunch. Or, you know, it simplifies. It's one of those like kind of, it's a generalization that allows you to make the hardware a little bit easier. And even then, like that is part of the great thing about doing that kind of, it's like as a design decision, that's why people see it and they're like, oh, that's a great idea. And they catch on to it as, you know, because it's flexible, but it also eases the design a little bit more and allows you to consolidate. And even then, they're friggin' huge and take like
years and
huge amount of time to build.
They take like 5 years to
early
build a computer
when there's like no infrastructure to do it.
So here's something to consider. Having a stored program computer is conceptually more simple than a special purpose computer. Because a stored program computer, and this is something I didn't even talk about with Mad Ida, but the crew that worked on Mad Eye posits that they were another independent origin point for the idea of using binary algebra to describe logic circuits. If that's true, then that means that Zeus, Stibbits at Nassau, these guys at Northrop, and I think 2 or 3 other people came up with this idea independently, right? But the point I'm getting to here is if you have a general purpose computer, a stored program computer specifically, you can just describe it in terms of your instruction set, right? So cognitively, it's a smaller load. You have a machine that operates or that executes these instructions. It operates on data of this format. A special purpose computer, though, has to have specialized circuits. So conceptually, that's more difficult to work with, at least I think, because it's not generalized. You can't use the same kind of, like with the general purpose computer, a lot of the descriptions are really repetitive. We use a NAND gate, or we use like an exclusive OR gate, and we have this array of them, that's an adder. It's not, I have my special adding circuit, I have my special timing circuit, I have like all of these special things that you have to use together with this esoteric drum rotation logic, and then you get an integrator. It's, we have a NAND gate.
I see your perspective. I think it's a little bit of both, and I think it also depends on where you're at in the history of kind of the corpus of knowledge being built up for this kind of stuff. Because I can't prove it, but it feels like
then
early
that means
on.
It's a perfect thing to discuss.
Yeah. It feels like my read on it is that earlier on, again, like, from the 40s, logic circuits and, executing an arbitrary, like, mathematical operation or series of mathematical operations in hardware is it's kind of too broad to say not a solved problem yet, even though it kind of is, but there's no library. Again, there's no corpus. They're developing the corpus of knowledge and the building blocks for these things, right? And
they're finding adding circuits in random desk drawers.
That is literally true. And even beside the adding circuits, one of the big things is the control mechanism of things. Because for a bunch of stuff, it's actually like when you read these papers, the thing that they're focusing on, and it makes sense because their intent is to build an automatic calculator, is they're focusing on the math circuitry.
Yeah.
In particular. And those are relatively easy to define in that you can do like a pretty straightforward mapping between how the mathematical function should operate and, building an equivalence in Boolean logic, and then being able to prove that they are mappable to each other, and therefore we have a Boolean equation that we can, implement in circuitry, bada bing. But you get into control stuff, and that gets into sequential logic.
Which isn't,
which is not
with algebra. Okay.
Yeah, it's a little more complex, and so
you need APL.
I feel like this is the thing: is people, especially when you're focusing, like when you're starting to learn low level of like how CPUs operate or whatnot, which like everyone eventually, you start out learning to program, and then you get more interested, and then you're like, what's this ALU that I've heard so much about? And like something like that, the ALU gets like so focused on, but like way later in the game, solves problem. A bunch of the stuff is just the all around it, the driving it and the state machine around it, which brings me back to like the microcode thing. And figuring out that I've a wide microcode, and then that just becomes part of the corpus, right? But like microcode at all being a thing, not really until mid 60s, 360 comes out, they develop this as a thing, and then it becomes a super common mechanism. But anyway, as my Joe Blah on design things goes on, the ultimate kernel of my thing here is that I think at the beginning they did not have as a building block. And this is something I could look up if I had a minute, so I'll try to and get back to you. But that the idea of a state machine wasn't really there yet, particularly a finite state machine, which is the building block of like
incorrect.
Incorrect?
Incorrect. Church Turing thesis is literally a state machine.
Right, but is it described as such?
Okay,
because like as far as it being an electronics engineering building block that is like just part of the again like the lexicon, the book of tools that all engineers have. I'm curious when that starts to become a thing, only because I get this read that like early on.
Article on state machines does not have a history section.
Annoying. Because that's the thing is later on, like you get a very a great engineering process for it because it's just like you define the states of your machine and it is then very easy to break down into a sequential series of registers and building blocks, and then eventually that just turns into Verilog because that's all something like Verilog or HDL does.
Counterpoint, Joe. What I'm hearing, nothing you said. What I'm hearing is over time we get more tools for stored program general purpose computers because we get more of them, right? Like more is being developed. I still think that proves my point that conceptually GP machines are much more simple because special purpose machines, they're unique. There's no corpus that's ever built. You get one.
That is,
and then another one shows up.
You're not totally wrong there. Really, I'm not a disagreement. It's that what has been tossing around my head every time you've said that, that I haven't gotten a chance to say that yet, is that I think there is definitely a tipping point where a more complex general purpose machine can be more complex than a fixed purpose machine can be more complex than a general purpose machine, but that with a general purpose machine, it is built around the particular state machine of executing instructions, right? And then it can do whatever. It's just a question of time. Whereas with the general purpose machine, you might have a very simple, what boils down to a state machine that executes the sequence of operations, pull the number off the track, add it to the number on the other track every so often, blah, blah, write it back to the track. And that may be a much simpler state machine than the load instruction, do operation, store data cycle. But then you might have a much more complex state machine because you are doing a more complex set of operations. So over here, you kind of don't have a scale, right? It's just like you have that state machine and you're building something around the complexity class of that kind of state machine. Whereas over here, it has a whole range from a state machine that is more simple than that state machine to way more complex.
You see, you're just convincing me that special purpose machines are more interesting because there's more variety.
I think we agree on that from the start. And
from the jump.
From the jump. That's what we said, is that they're with a general purpose computer, all you got is the surrounding story that makes it interesting, or how it does it, like its particular optimizations or whatever, but that what it does is not a particular interesting thing. You get something like Mad Ida, and what it does is as interesting as how it does it. Because again, I mean, as the wrap up here, as we hit about an hour, I'm looking at the clock. The whole thing about Mad Ida is that it does this job of differential analysis and does it real good, and that's its job, and
that's it.
And that's it.
Nothing else.
And the fact that we're
not even binary to decimal conversion.
No, plug in your oscilloscope. What are you doing? Oh, let's close out with a banger. You know what those track selection switches are?
What?
Octal.
Oh, really?
Now, this is also a classic Jonas, but I give you about 80% confidence on that. Firstly, because I always underestimate, my big reading thing a month or two ago was that EDVAC paper, and they do everything in octal in that thing. And that's the EDVAC paper, that's like one of the first papers. Right. And 2 to 7 and 0 to 7. I mean, I'll give you this one. This isn't like a fun gotcha. This isn't going to be one of my best gotchas, but 44 tracks, right? Yeah. So they select the track, 2 octal digits. gives you up to 64.
And
you know that one of them is truncated
right.
because you've got the one switch that starts at 2, which for whatever reason, now that part seems backwards, right? Like that's kind of weird, but that would be really easy math to do that actually I probably should have done ahead of time. But I bet you that is,
I think you're totally
closer
right,
to 44 than 64.
That's funny.
Yeah, I forgot I had that one to drop. That was one that was in the back of my head.
There's nothing in the sources that say what bit width it is besides there's 18 bits on a track. It's never like, we use octal. It's like, no, you read it on the scope. It's a number.
Yeah, and I feel like it's one of those things where, again, you get into like the mechanical details of things because the only drivers when you're building anything are not just the idea of the thing. They're like okay, now how do we physically realize this in a way that's workable? And one of those things is like to do octal, you can do it on a rotary switch pretty good because there's 8 positions and each of those positions is just going to connect one of 3 wires to ground or not or something like that.
Gotcha.
So it's just a wiper rotary switch, and it's a pretty solved thing in the 40s.
Interesting.
Yeah, I
gotta keep my eyes open for octal in the 40s now.
Yeah, it's just that it mainly stands out to me and punched me right in the face when that came up in the episode because I hadn't quite been aware. I know octal goes back, but it goes back like all the way. And the fact that it goes back the way is actually like really rad and a thing that I didn't understand in that way until I was reading that EdVac engineering paper.
Well, Joe, I'm gonna be looking out for the number 7 for a while now.
I think that's the thing too. That's one of those like magic number things that when you see a 7, once you've been octal brained, you're like, it's octal. I see a lot of 7s. There's octal in here somewhere.
I'm just gonna see that next time I see a bill. Just like a bunch of 7s, this is an octal, right? This is a lot less.
Why do they expect me to do these conversions? Well, it can't be that bad, I'm sure. Well, anyway, on that note, I'm glad that for all my hemming and hawing on trying to remember topics that were things that I wanted to discuss, I managed to come up with that at the last minute. So thank you, everyone, for joining me on that journey. And please go out, think more about, the weirdness that are fixed purpose computers. And as always, on the Discord, tell us how we're wrong.
And melt something in toluene.
Safely.
Post your photos on the Discord of things melted in toluene.
Tell us why I think silver dip is toluene. I still think it might be. I'll look it up after this.
Yeah, we got to figure it out.
Diarrhea. Probably wrong. Anyhow, we'll catch you next time, and I will drop that again. Sean's got his plugs on the main channel, which is this thing, and then I've got the subsequent plug of track down our Discord. It's somewhere. I'm not gonna.
I'll link it.
Yeah, there you go. You can link it. But I know people can find it because the last time that I said that, people popped on, so it is findable.
It's because I linked it.
Probably. That would make a lot of sense. And yeah, we have really good discussion there. I have been trying to, again, after we post these episodes, I try and prompt a little discussion there. And people tell us, again, that's where I came from, is wonderfully, and the most wonderful kind way, how we're wrong. And we have a whole great conversation about it. And it's awesome. And that's why I started this show, so I get it. So see you guys around, and we'll see you
around
on the next Adjunct of Computing.